Dear friends, today we will study about the Wheatstone Bridge. Wheatstone Bridge was developed first of all by Charles Wheatstone, and it is only a network of four resistances PQRS as shown in figure. Now, Charles Wheatstone developed this bridge in order to find the value of the unknown resistance, and he found the balancing condition using Kirchhoff's law for electrical circuits, which is very important, useful in the application of the Wheatstone bridge. So, this figure shows a Wheatstone bridge, and when no current flows through the galvanometer, that means between the point B to D through the galvanometer, if no current flows, then that condition is known as balancing condition. And in Wheatstone bridge, this condition is must, then only we can use it to find the value of the unknown resistances. If the resistance of the the value of the other three resistances is known. Here I have taken this resistance as P, this resistance as Q, this resistance as R, and this resistance as S. A potential difference, a source of with the help of source of EMF, is connected between point A and C. So a potential difference is created between points A and C, and consider a total current I flows through the whole of the circuit, but according to Kirchhoff's law, it divides at point A. Let the two values, the two currents I1 and I2 from I, they flows through resistance P and R respectively in the two branches, as we know that it divides according to the resistances. The current divides if the two resistances are connected at the same point. So from P to B, let this current be I3, B to Q, and a current IG flows through the galvanometer, and through S a current I4 flows through, and at point C I3 and I4, they meet and makes current I. Here I4 is equal to I1, I2 plus Ig, and I3 is equal to I1 minus Ig. This should be very clear that if we consider from B to C, the current flowing is I3, this will equal to I1 minus Ig, I1 minus Ig, and I4 current which is flowing through S is equal to I2 plus Ig. Ig and I2, they will add up and that flows through S. So this should be very clear that the total current, if we add I1 minus Ig plus I2 plus Ig, this is equal to I1 plus I2. So this is about the distribution of the current. Now we find the balancing condition. Now if we apply the Kirchhoff's laws in mesh ABDA and in mesh BCDB. So first we apply the Kirchhoff's second law in mesh A, B, D, A. So here I1 is clockwise, I2 is anti-clockwise and Ig is clockwise. So I1 and Ig is taken as negative whereas I2 is taken as positive, and we can write the equation minus I1P minus Ig into G plus I2 into R is equal to 0. Here I have taken 0 because there is no source of EMF. The potential difference is 0 or the EMF is 0. Now for mesh BCDB, here Ig is anti-clockwise, I4 is anti-clockwise, I4 means I2 plus Ig, and I3 is clockwise. So I3 is negative, I3 is equal to I1 minus Ig, this is negative, and Ig is positive, I4 is positive. So we can write the equation for mesh BCDB I1 minus Ig into Q minus plus Ig into G plus I2 plus Ig into S is equal to 0. Or minus I1 into Q plus Ig into Q plus Ig into G plus I2 into S plus Ig into S is equal to 0. This is equation 2. Now as Ig for balancing length, no current flows through galvanometer G, that is Ig is equal to 0. Hence from first and second equation we get I1P is equal to I2R and I1Q is equal to I2S or P by Q is equal to R by S. Now, if we see the diagram, if no current flows through the galvanometer, then I3 is equal to I1 and I2 is equal to I4. So simply we can say this is ineffective. And if this condition exists in such a network, then no current flows through the conductor. And therefore we can say that if out of these four resistances, if the value of 3 is given, we can find the value of the fourth one, and this is used in meter bridge to find the value of the unknown resistance.